And today, as you can see from the lesson in front of you, is looking at rates of change. Really what that means is in grade 9 you talk about linear functions. In grade 10 you talk about quadratic. And now we've talked about exponential. And so we're just going to kind of look at how you could tell when it's one versus the other. And that activity that we did yesterday, this activity that we looked at yesterday, so comparing linear growth, which looks like that, okay, to quadratic, which looks like that. And let me stretch this out a little bit better than yesterday. And we know what parabolas look like. We have a really good idea of what they look like. Okay, versus exponential. And how does that look different? And this only shows the positive side. Whoa, gets big fast. But what's really interesting, I think, is when we compare all of them. Oh. Okay, and so we can see that, in fact, when exponential gets big, you can hardly even see that that's quadratic. But if I zoom in, you can see that this one is curving, it's quadratic. This one's linear, it's straight. And so the graphs all look different, and they all have different kinds of growth. And a big part of what that means is they model different things in the real world. And part of the practice that you're going to have, we'll talk about that a little bit maybe, but part of the practice that you're going to have will be thinking a little bit about how that, how you would use these in real world. What kinds of things get modeled by these different types of growth. And that's the whole point of mathematics, right? A lot of people ask, when am I ever going to use this? What's the point of all this? This seems silly. But it models the real world. Lots of things in the world grow linearly. You might never do this, but like something as simple as if you're buying bananas. If you buy one banana, it costs you, I don't know, 20 cents. You buy two bananas, it's going to be 40 cents. You buy three bananas, it's going to be 60 cents. Right? 20 cents per banana or whatever it would be is linear growth. The more bananas you buy, the more money it's going to cost. And it would be, they might go by weight, but you understand what I mean, right? Or cookies, if you buy cookies and they're 25 cents each. So 25 cents per, you buy more cookies, you pay more money. Okay? And then quadratic, what's something that follows quadratic? Well, gravity. So when you throw something, it follows a parabolic path. It's quadratic, right? And that would be an upside down parabola. That's a really common, really easy one, and you've seen that lots. And then in grade 10, you do all kinds of stuff with quadratic. So all those other word problems and applications that you've done are all quadratics, right? And then exponential. And we looked at some sort of made up examples of exponential growth when we talked about those stories. But money, interest. So interest is how many people have a bank account? So you get a little bit of money on a savings, a little bit of interest on a savings account, not very much, but you do get a little bit, and that follows exponential growth. Problem is the interest rate is the interest rate is so low that it never really gets to the point where it starts skyrocketing. So it always kind of grows slowly, which is the unfortunate part, but it is exponential growth. And there's lots of other things in the world that follow exponential growth. Bacteria growth, sometimes populations of mammals and people follow exponential growth. Exponential decay there's a really famous example of that called half-life. So like exponential growth and decay is also really, really common in the real world, and simple stuff, not like high-end stuff, relatively simple stuff. So that's the idea of what we're comparing today, and what we're doing today is comparing these three different kinds of growth. And we're going to do it three ways. So one of the obvious ways is we're obviously looking at a table of values, but we're going to actually look at it in three different ways. So let's fill out the first table of values. So again, and filling out a table of values is something that should be very straightforward, but if you forget how to do it, we did it yesterday, but you always just take this number and plug it in for x, and evaluate it. So this first one would be like 2 times negative 3, which is negative 6. But you don't have to show that every single time. So 2 times negative 2 is negative 4. 2 times negative 1 is negative 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. And I can use that to plot the graph. That's often what we do, but there are other things that we can do with this. Now, what's interesting, for us, we built this based off of an equation. So everything works out perfectly. But in the real world, it wouldn't be like that. In the real world, what you might do is you might gather a bunch of data somehow. Maybe you're standing on a corner measuring how many people walk by or asking them a question and collecting survey data that way. Maybe you have some kind of electronic measuring device that's measuring something or other, okay? And all those measurements would go into a table. So it wouldn't be based off of an equation. It would be based off of data that you've gathered. And you could still do the following kinds of things. You still graph it. You'd probably do it with a computer. You could still do what we're going to do with it. So what we're going to do, excuse me, is we're going to use what's called finite differences. We're going to find differences and ratios between the values to determine the type of growth we're looking at. So what we always do is you think about what's happening. Let's do it this way first. What is the change if I go from negative 6 to negative 4? How have I changed? An increase of 2. I love it. Perfectly said. And I'm going to show the increase by saying plus. So that's plus 2. The way you would calculate it, actually, let's wait. So what about negative 4 to negative 2? That's also plus 2. From negative 2 to 0, that's up 2, or an increase of 2, so that's plus 2. From 0 to 2 is up 2, so plus 2. From 2 to 4 is up 2, so plus 2. If it wasn't as obvious, if you couldn't just do it in your head, like we can just see what's happening there, you always do the lower one minus the one above it. So it would be 4 minus 2, not 2 minus 4. Okay, not 2 minus 4. It would always be the lower one minus the one above it. Have to. Okay, so that's one thing you got to remember. And from 4 to 6 is up 2, so plus 2. And what do we see? They're all the same. They're all exactly equal. Exactly equal. Not just, if it was real life data, you'd probably just be estimating. So they're about the same. But for us, since it was based on the equation, they're all exactly the same. So they are all equal. Therefore, this function is linear. That's what we conclude. And you've seen this before. This is not new. You've seen this before. You may not remember it. You don't do it a ton, but you've seen it. Okay, let's do the next one. Now this is negative 3 all squared. So it gives me 9. Positive 9. If you punch this into your calculator wrong, calculator would tell you negative 9. So you have to kind of know either how to punch it in with brackets or just know that it's going to be a positive. Negative 2 squared is positive 4. Negative 1 squared is positive 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. And again, we're going to find the differences. So from 9 to 4 is what kind of a change? So on your calculator, you could do 4 minus 9. You don't do 9 minus 4. Some people always get in a habit, and this goes back to grade school, of always doing the bigger minus the smaller. But make sure you don't get in that habit. Sarah? Well, which one is it? 5. And which direction? Did I get bigger or smaller by 5, going from 9 to 4? Smaller. So I went down 5. So we're just going to put a negative sign for that. Okay, so down 5 means negative 5. That's what we mean. From 4 to 1 is down 3. From 1 to 0 is down 1. From 0 to 1 is up 1. From 1 to 4 is up 3. And from 4 to 9 is up 5. What do you see here? A pattern. And some people are like, oh, there's a pattern. No, we're not looking for a pattern. We're looking for them all being equal. So in the first case, they were all equal, linear. In this case, they're not. So what do? We do it again. Okay? So from negative 5 to negative 3, we do it with these ones, though, this time. What's negative 5 to negative 3? Increase of 2, up 2, plus 2. Negative 3 to negative 1, up 2. Negative 1 to positive 1, up 2. 1 to 3, up 2. 3 to 5, up 2. Now that we've done this twice, we can talk about this. This is called first differences. Whoops. If I can spell differences. And this is called second differences. And if the first differences are all the same, it's linear. If the second differences are all the same or all equal, then what do we conclude? We conclude that this, does anybody know what, well, you already know because of the equation, but this one's quadratic. That's what that tells us. Okay. Any questions about that? That is all review. You've seen all of that before. What we're going to do next will be a little bit new. Everybody good? So first differences, all equal, linear. Second differences, all equal, quadratic. And you could do third and you could do fourth. We won't in this course. In other courses you would. But that's different kind of stuff. For us, we can stop at 2. What's the other possibility? So let's take a look at this one. We already hopefully know what kind of a function this is. So this is 1 over 8, which works out to 0.125. I think we want the decimals for this. You can do fractions. Depends on how comfortable you are. You're going to punch these into your calculator probably. That's 1 over 8. This one's 1 over 4, so that's 0.25. This one's 1 over 2, because it's 2. I'll show you why. We did this yesterday, but it's 2 to the negative 3. I'm going to erase this though, which is 1 over 2 to the 3, which is 1 over 8. And 1 divided by 8 gives me that, right? And so this is 2 to the negative 1, which is a half, so 0.5. 2 to the 0, again, we talked about this yesterday, is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the 3, or 2 cubed, is 8. So 1 over 8, 1 over 4, 1 over 2, 1, 2, 4, 8. Same as what we saw yesterday. And now, it's already a little bit trickier. Can't do it in my head. So I'll use my calculator. I'll go 0.25 minus 0.125. So this one gave me 0.125. And I'm just going to put here what I did. I did 0.25 minus 0.1. Actually, I'm going to do it in a different color. To get that. 0.5 minus 0.25 is 0.25. 1 minus 0.5 is 0.5. Some of these you might be able to do in your head. If you can, great. 2 minus 1 is 1. 4 minus 2 is 2. And 8 minus 4 is 4, or it's an increase of 4. I should have my signs in there, right? If it's positive, we don't have to write the positive, but this is an increase of 4, an increase of 2, an increase of 1. You can think about it that way now. Is that good? What do we notice? There is something interesting happening here. You may have picked up on it. Like, what do you notice? Anything? No? Kind of jumps out at me. Yeah. But they're the same numbers, aren't they? Like, I've just moved them all over it, but then we lost the 8 because, like you say, you kind of cut it in half. Yeah. But it's the same numbers. Kind of strange, but okay. But not all equal. Do we agree with that? So this is not linear, which again we already know, but it won't always be obvious. Do the same thing. 0.25 minus 1.25 is 0.125. 0.25, 0.5. This is an increase of 1, and this is an increase of 2. So it's done it again. I've got the same numbers again, but they kind of moved around. But again, not equal, so this is not quadratic. So what do? Now we stop subtracting and we go to the ratio and we divide. So I'm going to draw a line here so that it's kind of obvious. And I'm going to say, now we do a ratio, which is dividing, instead of subtracting. But I still do the lower one divided by the one above it. So this is going to be 0.25 divided by 0.125. Again, I'm going to do this on my calculator. 0.125 divided by, 0.25 divided by 0.125. And I get 2. .5 divided by 0.25. And that gives me 2. Two divided by 1, well, that's obviously 2. And that's the last one. So what happened here? Before we were subtracting, when we subtracted, we got the first differences. They were all equal. It was linear. Subtracted, got the second differences all equal. That was quadratic. This time we divided, so the ratio is all equal. Therefore, this function is exponential. Now, look up here for a minute. Put your pencil down and look up here. We could have done the dividing from the first row or the first column. We didn't have to do the first and second differences. So when you come across a new question that you have to do this for, you might look at the numbers and guess if it's exponential. You might even check a couple of them. And that would avoid you having to do these first differences and second differences, finding out neither of them work, and then doing the ratio. But if you don't guess correctly and you start with first differences, then you do second differences, then you can do the ratio with those, and check those instead of going, or you can go back and check the original numbers. But you can see that these are always doubling. 0.5 to 1, 1 to 2, 2 to 4, 4 to 8. So if I came across this table, which again, the ones that you're going to do won't be as obvious, but if you can tell just from looking that it's exponential, you don't have to do these. You can go straight to the ratio. So you can try one or the other, or you can just guess and try the ratios, and if you guess correctly, good. But if you don't, then you got to go back and do the first differences and second differences. And if none of them work, then it's none of them. And that happens too. There are other kinds of growth, or there might be no pattern. There might be no relationship. Okay, so if you try first differences, second differences, and ratio, and none of them work, then it's none. Now, if I got like 2, 2, 2, 3, I would be like, I probably made a mistake. I probably did something wrong. It's not, you would probably get all different numbers everywhere, whether it's differences or ratios. Okay? Any questions about that? So that's how you tell which type of growth or which type of function from a table of values. And you've seen first differences and second differences probably before, but you've probably not seen the ratio before. So that's what we're adding on. The other thing is, what is the exponent on the x of this function here? Anybody remember? There isn't one, so what does that mean? What is it? Nick, do you know? It's a 1, right. So this has an invisible 1 on it. So exponent 1 means it's linear. Okay, an exponent of 1 on the x means it's linear. An exponent of 2, as I hope we know, means quadratic. An exponent of 2 on the x means it's quadratic. And it's not the point that, well, why did we do the table of values if we already knew what it was? Well, because we're learning, right? Like, if you were given the equations, yeah, you can tell by the equation what kind of function it is. If you're not given the equation and you're only given data, then you have to do the first differences, the second differences, and possibly a ratio. And then we talked about this yesterday, if x is in the exponent, it's exponential. So now that was quick. We know how to find growth from a table of values. That took a bit more time, but we also know how to find what kind of growth or what kind of function it is from just the equation. So that's important too. That's kind of a big deal. And the other thing we're going to do is we're going to graph all these, and we're going to see what the graph looks like for each. So we'll do it quickly, but y equals 2 to the x. So if I go to -2, I go to -4. If I go to -1 is -2, 0, 1 and 2, 2 and 4, 3 and 6. So a linear function is a straight line. And that means when I look at a graph, at an equation, like this, I can tell by the exponent that it's linear, and I know it's going to be a straight line. Okay. Next one is the quadratic. So it was just y equals x squared. So 1 and -1. 2 squared is 4. -2 squared is 4. 3 squared is 9. 4 squared would be 16, so I can fit another point on here, so I might as well. So this one is y equals x squared, and it's a parabola. And remember, if it's an exponent of 2 on the x, we know that it's quadratic. We know it will make a parabola. Like, that's something we just should know, be able to recognize it from the equation. And then the last one is our exponential. So -3 and 1.125 is very small, so I'm just going to go very small here. And then 1/4 is -2 is 0.25. -1 is 0.5. And 2 to the 4 is 16. It's very interesting to me how y equals x squared and y equals 2 to the x have all these similar points. Okay, and this is y equals 2 to the x. And it has that increasing or decreasing look to it. It doesn't curve back up. Some people says it looks like a J or an L, kind of like that, okay? And that's how you could recognize, like, what if I just gave you the graph and you had to decide which of the 3 it was? Well, if it's a straight line, it's linear. The equation would have an exponent of 1. If it's a parabola, it's quadratic. The x would have an exponent of 2. And if it looks like that exponential curve that's always increasing or always decreasing, then it's exponential. So we have determined how we can find what type of function it is from a table of values, from the equation, and also from just the graph.